Dear students, welcome once again in the class of topology. We have done a lot in separation axioms T0, T1, T2 spaces, T3, T3 and half spaces, T4 spaces, Urysohn's lemma and many more things. Completely normal spaces are left we are with. So I'm going to start with completely normal spaces. So what are the completely normal spaces? First of all, definition. So this is the definition of completely normal spaces. So let X top be a topological space. Let X top be a topological space. X top is said to be completely normal. I'm using the abbreviation CN for completely normal. So X top is said to be completely normal if for every pair AB of separated subsets of X, there is a pair of disjoint open subsets GH of X such that A is contained in G and B is contained in H. So here is the definition of a completely normal space. If you take any two separated subsets of X, if the space is completely normal, you will always be able to find a pair of disjoint open subsets G and H of the same topological space X such that A will be contained in the set G and B will be contained in the set H. So this is the definition of completely normal space. And one more thing that is really important is that, like you know that if a space is normal as well as T1, it is called T4. Similarly, if a space is completely normal as well as T1, then it will be called T5 space. Oh, what are T5 spaces? T5 spaces are the spaces, topological spaces, which are completely normal as well as T1. So here was the definition of completely normal spaces and T5 spaces, and now we are moving on to the first theorem of completely normal spaces. So here is the statement of the theorem. Every completely normal space is normal. This is the statement, and before moving on to the proof, let us discuss something more. What we are going to prove? We are going to prove that if a space is completely normal, then it is normal. This is what we are going to prove in this theorem, that a completely normal space is always normal. Now, if a space is completely normal and T1, that means complete normality implies normality, and T1 it is already. So if a space is Cn completely normal plus T1, then it is normal plus T1. And we know that complete normal plus T1 means T5 and normal plus T1 means T4. So that means this theorem will automatically imply that every T5 space is T4. If a space is T5, then it is also T4. So till now what we have seen, if a space is T5, then it is T4. If a space is T4, then it is T3 and half. If it is space is T3 and half, then it is T3. If it is space is T3, then it is T2. If a space is T2, then it is T1. And if a space is T1, then it is T0. So it is a cycle. T5 implies T4, T4 implies T3 and half, and so on. We move up to T4, T0. This is a cycle these results we have already proved in our previous videos, and this result will be automatic if you will prove this result what we have stated in this theorem. So this theorem we are going to do, and this will complete the cycle. So how to start the proof? We are given that the space is completely normal. So let x top be a completely normal space. We have taken a completely normal space, and what we want to show that it is normal. And if we want to show that it is a normal space, from where we have to start? We will have to take a pair of disjoint closed subsets of X, and we will find a pair of disjoint open sets containing them. So I'll start the theorem by taking a pair of disjoint closed subsets of X. So let A, B be a pair of disjoint closed subsets of X. A and B is a pair of disjoint closed subsets, means A intersection B is 5 first of all. Secondly, A is closed. So A is closed, that means you can say A bar is equal to A. Closure of a closed set is the same set. And B is also a closed set, so that means B bar is equal to B. Now look that there are two things. A intersection B is 5 and A is equal to A bar. So here you can replace this A by A bar. So A bar intersection B is 5. Again, I am deleting it from here. A intersection B is 5 because A and B are disjoint, and B is equal to B bar, so you can replace B by B bar. So what you have seen that A bar intersection B is 5 and A intersection B bar is also 5. That means A and B are separated sets. So this means A, B are separated sets. And if A, B are separated sets, then as we are given that the space is completely normal, there will definitely be a pair of disjoint open sets G and H containing A and B. So therefore, there exist open sets G and H such that A is contained in G, B is contained in H, and G intersection H is 5. Now look at from where you have started and at what point we have reached. We have taken a pair of disjoint closed sets A and B, and we have obtained a pair of disjoint open sets G and H containing them. Is it not the definition of a normal space? Yes, it is. So that means the space X tau is normal. So this implies X tau is a normal space. We have taken a completely normal space and we have proved that it is a normal space. That means every completely normal space is a normal space, and it also proves that a T5 space is a T4 space. Now we'll move on to some properties, some theorems related to completely normal spaces, like topological property, is it or not, hereditary property, is it or not, etc. So the second theorem on completely normal spaces, I am going to take it is theorem, write down the statement, prove that complete normality normality is a hereditary property. That means we have to prove that if a space is completely normal, then every subspace of it is also completely normal. So how to prove that? So let us start with the proof. Let X tau be a normal space, be a completely normal space. Let Y tau Y be a subspace of X tau. So what we are to show? We are to show that Y tau Y is also a completely normal space. And for that, we will have to take two separated subsets of Y, and we will have to find two tau Y open sets containing them. So let us start. Let A, B be separated subsets of Y. That means A Y bar means closure of A in Y, closure of A relative to the subspace Y, intersection with B is phi, and A intersection with closure of B in Y is also phi. From our previous knowledge, we know that A Y bar means closure of A in Y is closure of A in X intersected with Y. Similarly, closure of B in Y is closure of B in X intersected with Y. This is from our previous results of topology in the first or second chapter, where you have studied closure of subsets, etc. Now these results I am going to use here. AY bar, I am substituting the value here. So what you are going to get from here is AX bar, closure of A in X intersected with Y intersected with B is phi, and similarly I am going to use it here. A intersection with closure of B in X intersection with Y is phi. Look at now what it implies, what it gives. Here AX bar, that means closure of A in X, I have written as it is. And what is B intersection Y? Because B is a subset of Y, so B intersection Y will become equal to B. So it is intersection with B is phi. And similarly here, and here it is B, closure of B in X, and A intersection Y. Since A is a subset of Y, A intersection Y is equal to A, so intersection with A is phi. What we have obtained now, closure of A in X intersected with B is phi, and A intersected with closure of B in X is phi. That means A and B are separated sets in X tau, but X tau is given to be completely normal. In a completely normal space, if you are having two sets A and B which are separated, then you must have open sets G and H. So therefore there exist open tau open sets, you can say. So therefore there exist tau open sets G, H such that your A is contained in G, your B is contained in H, and G intersection H is phi. This is because A and B are now separated sets in a completely normal space X top. Now, G is open set, Y is subspace. So if you intersect G with Y, G is tau open. If a tau open set is intersected with Y, a subspace, it will become tau Y separated set. So tau Y open set. So this G, which is tau open set, when it is intersected with Y, let it be G1, then G1 will be tau Y open set. Similarly, if this H is intersected with Y, let it be H1, then H1 will be tau Y open set. So G1 and H1 are tau Y open sets. Since intersection of G and H is phi, and G1 is a subset of G, H1 is a subset of H, so if two sets are disjoint, definitely their subsets will also be disjoint. So that means G1 intersection H1 is also phi. Now, your A is a subset of G. A is also a subset of Y. A is subset of G. A is also a subset of Y. So that means A is a subset of G intersection Y. Similarly, B is a subset of H intersection Y. But what is your G intersection Y? Your G intersection Y is G1. So A is a subset of G1. Similarly, B is a subset of H1. You have started with two tau Y separated sets A and B, and now you have obtained two tau Y open sets G1 and H1, such that A is contained in G1, B is contained in H1, and G1 intersection H1 is phi. This means your subspace is completely normal. So this implies that Y along with the topology tau Y, the relative topology, is a completely normal space, and it proves the hereditary property of completely normal spaces. So this was an important theorem, an important property you can say about complete normality in separation axioms, and another important property is topological property. So now let us have a theorem related to that one. So the theorem is prove that complete normality is a topological property. Complete normality is a topological property. Earlier we have shown that it is a hereditary property, and now we are going to show that it is a topological property. Topological property means we will have to show that homeomorphic image of a completely normal space is also a completely normal space. So I'm going to start the proof. Let X tau be a completely normal space, and let F from X tau to another topological space Y rho be a homeomorphism. Homeomorphism means it is 1-1, it is onto, it is continuous, and it is open. Homeomorphism means function is 1-1, onto, continuous, and open. Or you can say 1-1, onto, continuous, and F inverse is also continuous. Or you can say F is 1 1 onto continuous and closed. So any one definition you can use. Here I am going to use 1 1 onto continuous and open. So this is a homeomorphism I have taken. This is a completely normal space, and I will show that Y row is also a completely normal space. If I am to show that it is a completely normal space, I'll have to take a pair of separated sets from Y row, and then I'll have to find a pair of disjoint open sets containing them. So I'm starting with let A, B be separated sets in Y row. That means A bar intersection with B is phi, and A intersection with B bar is also phi. Since f is a continuous function, f inverse A closure of it will be a subset of f inverse of A closure. From the chapter of continuity, third or fourth chapter, you can say f inverse A closure is a subset of f inverse of A bar, and similarly f inverse of B closure is a subset of f inverse of closure of B. Now look that I need space, so I'll have to rub it. Your f inverse A closure is a subset of f inverse A bar. So what about f inverse A closure intersection with f inverse B? It will be a subset of f inverse. Here I am using the first property, so it is a subset of f inverse A bar intersection with f inverse B, which is nothing but f inverse A bar intersection B, and f inverse A intersection B, A bar intersection B is phi, so it is f inverse phi, you can say phi. On the same lines, you can show that f inverse A intersection with f inverse B bar is also phi. Now, closure of f inverse A intersection with f inverse B is phi, and f inverse A intersection with f inverse B closure is also phi. So this means f inverse A and f inverse B are separated sets in X top. Now you are having two separated sets in X top, but X top is given to be completely normal. In a completely normal space, if you are having a pair of separated sets, definitely there exists a pair of disjoint open sets containing them. So therefore, there exists disjoint open sets in top, say G and H, such that your f inverse A is a subset of G and your f inverse B is a subset of H. Now, this implies, this gives A is a subset of f of G and B is a subset of f of H. Also, f of G intersection with f of H is equal to f of G intersection H. Why? Because f is 1 1. It was a homeomorphism, so it was 1 1 also. So from 1 1ness of f, you can have this. But what about G intersection H? Your G intersection H is phi because G and H are disjoint. So it is f of phi, and f of phi is phi. So from where you have started, you have taken a pair of separated sets in Y, namely A and B, and now you have obtained a pair of disjoint open sets. Why open sets? Because G and H are open sets and the map F is also open. So that means FG and FH are open in Y. So you have a pair of disjoint because of this property. So you are having a pair of disjoint open sets F of G and F of H containing the separated sets A and B, and this implies your space Y rho is completely normal. That means homeomorphic image of a completely normal space is completely normal space, which means complete normality is a topological property. So here with this theorem I am going to stop this video. In the next video we will have more theorems on complete normality. Till then, thank you once again.